Welcome to the Windshield Chronicles, a mental sequence of operation. This episode brought to you by the Nexstar Network and NexTech Academy. Visit nexstarnetwork.com for more information. Hello everyone, thank you for joining Windshield Chronicles. We're spending some time today with Joe Delong of Nexstar and NexTech Academy. Joe, thanks for joining us.
Thanks for having me, Clifton.
Let's go through a mental sequence of operation for a gas furnace. So say we're heading out to a call for a no heat, and let's pick on a basic furnace. Let's just say a Goodman single stage furnace. And walk through a mental sequence of operation through the entire wiring diagram so that we can prepare for this job before we get there.
Absolutely, sounds good. So in this situation, we're on our way to a call. We got a no heat. Clifton just said we got 80%, 80,000 BTU single stage Goodman. No heat. We arrive at the call. Filter's clean. That's looking good. We're going to turn the thermostat on. We're not hearing anything happen downstairs when we go to the basement or look at the furnace. So first thing we're going to do is we want to go down there and open up that bottom panel door. If we're looking at a furnace that's sitting vertical in a basement, for example. And when we open up that bottom panel door, we want to make sure our door switch is closed.
Blower compartment.
Yeah, the blower compartment.
Because it could be the upper door if we're in a counterflow position.
Yes, that is correct. That is correct. So let's get the blower door open for that furnace. And, you're going to need to get either some tape or you're going to need to get some like a magnet. The magnet switches are nice to make sure that door switch is closed, but that's going to have to be in place in order for us to be checking power and voltage. So when we go through the sequence of operation, let's start by looking at our disconnect. So we have L1, we have ground, and we have a neutral. Okay, just to make sure everything's going good on the power side, it's never a bad idea to open up that disconnect and check for, tight connections inside that disconnect box. Make sure you don't have any burnt or loose connections. And then leaving that disconnect box, we're going to go into the junction box of the actual gas furnace. So when we open that up, you're going to see typically a black wire for your L1. You're going to see a ground coming in, and you're going to see a neutral, which is typically white. And you're going to see some wire nut connections that the installer made inside that junction box. Now, what we're going to want to check for is obviously we want to see if we have power coming in. Now, one of the easiest ways to tell is if the board is okay, you're going to see some type of an indicator light on that circuit board. What we're going to want to do is, following that wiring diagram, we're going to want that power wire is going to come from the junction box, and it's going to go directly into our door switch. Door switch is just like a light switch. It's either open or closed. So if it's open, if that door switch is open, we're not going to have any power going to our circuit board at all. Granted, we taped it or used a little magnetic switch to close that door switch. If everything's good there, that power wire is going to go directly into our circuit board, and it's going to go to an L1 terminal on that board.
And this is assuming that we have checked from ground to hot to make sure that we have proper voltage, from neutral to hot that we have proper voltage. And I always like to verify between ground and neutral to make sure that we do not have any voltage between ground and neutral, which could show that we have a potentially open neutral back through our electrical circuit.
That is 100% correct. And then what we want to do is we want to make sure that between L1 and ground that we have 120 volts AC. Also, if your neutral is burnt or it is loose, that is also going to cause a voltage problem. Another thing that you want to keep in mind, it's pretty rare to happen in like a residential setting like this, is you want to make sure you don't have any voltage fluctuations plus or minus 10%. When we're looking at what our voltage is coming in. So when we follow our power wire coming into that board, that should be landing on what is typically an L1 terminal on your circuit board. That's going to be the same whether it's a two-stage furnace, whether it's a variable speed, whether it's a PSC motor. 95% of the residential circuit boards that are out on the market The power coming in is going to go to L1, okay?
Right.
Then you're going to see another wire that is labeled either L1 XFMR or it's going to be XFMR line.
Mm-hmm.
And what that is you got to remember that a board is just simply a series of inputs and outputs.
That's right.
So if we are coming in and we're supplying that board with the 120 volts AC that it needs, we have to make sure that that board is supplying power, sufficient high voltage power to our transformer.
Exactly.
So what that means is from our L1 terminal, between that and neutral, we should have 120 volts AC. Okay. Then when we look at the transformer terminal on that board,
Yep.
so from XFMR to neutral on the board, we also need to have 120 volts AC. So what that's telling me is that transformer is getting 120 volts from that input that's coming in from the power.
Directly through the control board.
Exactly, directly through the control board. So if we are in a situation where we had 120 volts between L1 and neutral on the board, and we had 0 volts between XFMR and neutral, that tells me that we have a bad board because the power is coming in, but we're not sending any of that power to our transformer.
Exactly. It's not passing completely through the board.
Exactly. So again, it's a series of inputs and outputs. So as long as we are getting power to that transformer between XFMR and neutral, that tells me the primary side of our transformer is getting voltage.
Has sufficient voltage.
Exactly. Now, granted, our transformer is good and we don't have any issues with that. Then we have our low voltage side. So we're going to have 24 volts and we're going to have a common on the secondary side of our transformer that's also going to have terminals on that board. And that should have 24 volts as long as the transformer is good. So if you walk up to a transformer, you don't see any LED lights or anything on that board. It's either a possibility that the fuse, the low voltage fuse that's also on that board is either blown or that transformer is bad. So that's another thing to keep in mind is nothing's going to work in here if we don't have sufficient line voltage power coming in that is also feeding the line voltage or primary side of our transformer. And then if the transformer is good, we're going to be able to supply that low voltage side or the secondary side of our transformer. As long as those two things are good and we don't have any low voltage shorts, we should be getting a diagnostic LED of some type on that board. Typically, it's like on most Goodmans, it's just a standard red light. If you don't have a call for heat and nothing's going on, it's probably just going to be a steady red light on that board. Now, at this point, let's just assume that our low voltage is good on the transformer. We have sufficient power coming into the board. Our thermostat is telling us that there is a call for heat. We need to verify that there's a call for heat. Okay. Right. Now, with this particular board, the system itself, and when I say the system, the board, the logic in that control board, the algorithm that's built into it, is going to constantly be checking all of the limits within this system. When I say limits, we may have a auxiliary limit that's a low voltage limit that's attached to the blower assembly. There could be one, there could be two of those. I've seen them where they have it on both sides of the back end of the or the front and the back of the blower assembly. Then you have your main limit or your high limit switch that's going to be attached to the firebox, the furnace. Then you're going to have your rollout switches. Those are going to be in place. Pressure switches. The pressure switches, the system's going to check to make sure that those pressure switches are open prior to a call for heat. Because if those pressure switches are closed, that's going to pop up an error code right off the bat. So the system is going through all of these different safeties within the circuit and constantly doing a check to make sure that those limits and the safeties and the pressure switches and all of that are closed or open, whichever their default is. And if that's all good, then you should be having a signal between common and W of 24 volts on that circuit board. What that's going to do is if everything's good to go there, the circuit board, once it checks all the safeties again, it's going to allow 120 volts to go to L1 and neutral for your induced draft motor. Terminal on the control board, if we follow it, you'll notice that the igniter, well, in this case, the igniter has its own terminal, but a lot of times on a single stage Goodman, you will see the igniter and the induced draft motor are typically on a 4-pin Molex.
Mm-hmm.
And when you look at the Molex, you'll see 2 white wires, 2 black wires. However, if you follow them, typically 1 black wire is going to go to your igniter, 1 black wire is going to go to your inducer, and then you got your 2 neutrals, 1 for each, the igniter and the induced draft motor. So the next sequence of operation, like I said, is once we have all of our limits and all of our pressure switches are closed, the induced draft motor is going to fire up. And in order for that to happen, again, inputs and outputs on this circuit board, we got power coming into the board, all the safeties are closed. Then we're going to, the circuit board is going to send 120 volts out of that Molex plug from the circuit board straight to the induced draft motor. The induced draft motor has to turn on. Now, granted, we have no issues going on with the induced draft motor, no issues inside the flue. Our pressure switch that is normally open will now close with the pressure provided in that induced draft motor in the heat exchanger.
Sure.
Once that pressure switch closes, okay, there's 2 things that have to happen at this point. Number 1, our pressure switch has to close once that induced draft motor is running. Okay. If that is good, the other part that needs to happen is the safeties have to continue to be closed or open, whatever their default is. The safeties have to be operating properly. Then the system will allow the ignition sequence to begin. That's when going back to that same 4 Molex plug, we are going to be now the circuit board is now going to be providing 120 volts out of that Molex plug directly to our hot surface igniter. Okay. Granted, that hot surface igniter is good. The next thing that's going to happen in that sequence is once our hot surface igniter lights up, the next part of the sequence is that gas valve is going to receive a 24 volt signal again from that circuit board. Granted, all the safeties are closed, it's going to send a 24 volt signal to that gas valve, allowing the gas valve to open. So then at that point, when we're following the sequence of operation, that gas valve opens. Now we should have flame present going across our gas train, across all of our burners, going from the side where the igniter is, traveling across our burners to the opposite side. Now we have to have flame rectification going on. So this is another thing that's very common in the northern states, if you're familiar with working on a lot of gas furnaces, is these flame sensors can get dirty. Okay. I want to say on average, and you can correct me if I'm wrong, Clifton, but I think on average, most systems need a minimum of 1.5 to 2 microamps of a flame sense signal in a gas furnace.
When I build my flame rectification circuit, it's just a simple diode resistor circuit to duplicate that flame rectification. I set that at about 1.5 microamps, and so far it's worked on pretty much every board that I've encountered.
Perfect. And you know, we can obviously discuss the flame rectification process and how to do all those checks in a separate podcast. Sure. And I'm sure you probably already have. But I have seen it to where on some systems in the field, before I clean that flame sensor, if I'm thinking it's a dirty flame sensor, by all means, verify. I have seen it where they're like 0.3, 0.5. Right. There's just simply not, they're just too dirty.
Right.
Now, granted, so I'm going to go back to that sequence again. So granted, we are getting a good flame signal. that flame sensor is going to allow our gas valve to stay on. Okay, so that gas valve is going to continue to send gas. We got flame. Flame sensor is sensing that flame. Now, while we are in this period right here, typically if we have our fan in the auto position, our blower motor is not turning on yet. So right now we are in what is called a heat on delay.
Correct.
Okay, now there is a heat on delay setting on our circuit board. These are going to be adjustable based on typically seconds. So 90 seconds, 120. It just depends on the manufacturer. It could be set in minutes. It's typically set in seconds. What that means is we want to allow our heat exchanger to heat up before we turn on that blower motor, so we're not blowing cold air into our conditioned space. So after that heat on delay, let's just say that we had a heat on delay of 60 seconds. The burners are going, once we have ignition and our flame sensor has proven flame, we are going to allow those burners to stay lit for, let's just say, a period of 60 seconds. Once that heat on delay ends, now the next spot of what's going to be happening in our sequence and on that circuit board is now we need to be sending voltage to our blower motor. So typically on the blower motor, now keep in mind in this scenario, we're dealing with a PSC motor, standard 3-speed motor. So we need to be checking for voltage, or you should have voltage between the neutral terminal and whatever your heating speed tap is set on for that blower motor. So let's just say we have it on low, let's see, in this case, medium low. So we have an orange wire coming out of our blower motor that's going to the circuit board for the heating mode of operation. We need to have power going between neutral and that orange wire. And that is going to be the voltage that we need to get that blower motor to turn on. Now, keep in mind, we're also assuming in this case that you have a good run capacitor for this PSC blower motor. If that is the case, and you have sufficient voltage, the next part of the sequence of operation is that blower motor needs to turn on. Now, real quick, I'm just going to break for a second here, Clifton, because there's something really important that I want to talk about here. So what I have seen from experience in the field that a lot of technicians have struggled with in the past is determining, okay, this is a bad board or this is a bad blower motor.
Right.
And I have seen that problem right there, or that confusion, come up quite a few times. So one thing I want to make very certain here is, one thing you want to make sure when you're trying to determine, is this a bad circuit board or is this a bad blower motor, is simply looking at the circuit board and checking for voltage between the neutral bank. And when I say bank, you're going to have a whole bunch of typically white wires
all clustered together.
All clustered together on a neutral bank. Check between the actual wire that is connected to the neutral for the blower motor, which is typically white, maybe another color though. Check between that and check between the heating connection speed tap on that board and verify that you have 120 volts. Okay, if everything's firing up on that entire system, and you got ignition and the heat on delay has ended, and you're not getting voltage between neutral and your speed tap for your blower motor, typically that's going to signal to you that you have a bad control board. Now, there's another step that I do in the field when I'm trying to verify that as well, is you can also put in a jumper or something going from your line voltage coming into your board, and leave your neutral connected, and you can actually get that blower speed tap and connect it to a line voltage source and see if the blower turns on.
Sure.
That's just another
bypassing the relay on the board.
Easy test you could do, which bypasses the relay on the board.
Sure, absolutely.
So I just wanted to touch on that real quick.
Absolutely.
Just to verify that it's either your board or the motor. Now, going back to the sequence of operation, let's assume everything's working again. Blower motor's running, burners are on. Now, at this point, we are going to be running the entire system until that thermostat satisfies. Now, another thing that the system is going to constantly be checking is checking for closed rollout switches, checking for a closed main limit switch. And if any of those things are off, that's going to break the whole sequence of operation and typically give you an error code on that board. Now, once the whole system, let's just say the whole system goes through and we reach the set temperature on that thermostat, the very first thing that's going to happen is the gas valve is going to open, which means we're no longer going to send a 24-volt signal to that gas valve. So the gas valve is going to open. The induced draft motor is going to run for a little while in that purge cycle that's predetermined from the factory.
Post-purge. Mm-hmm.
Post-purge, yes. And then once that happens, the blower motor will continue to run. So before we had a heat on delay, now we have a heat off delay. So one of the things that we don't want to do is we don't want to shut off the gas valve and shut off the blower motor all at the same time, because what's typically going to happen in that case is your heat exchanger is still very hot, and we don't want to shut everything off, because then what's going to happen is we're probably going to open up a main limit switch.
Right.
If we shut everything off all at once. So the heat off delay, 90, 120, 150 seconds, whatever that setting is on the board, which typically is adjustable, what that means is that the gas valve is going to shut off. We're no longer burning at the burners, and that blower motor is going to continue to run to get that heat exchanger cooled down, and that also provides hot air to go into the conditioned space after the burner shut down. Once that heat off delay ends, then the very last step of that is the blower motor will then shut down. And granted everything's still working again, that circuit board's going to sit there waiting for the next call for heat.
All right. Joe Delong, thank you so much for joining us, and we appreciate your time today.
Thank you.